Okay, so we did the 2 by 2 matrix problem. Let's do the 3 by 3 matrix problem. Okay, now we have 3 equations and 3 unknowns. Given y1, y2, y3, we're looking for x1, x2, and x3, and so there's this whole 3 by 3, our 9 element coefficient matrix. If we write it in matrix form, it's a little bit more compressed. And remember, the way that we do the multiplies is that this column hits each row in turn, and each element times element plus element times element plus element times element makes that upper row, second row, third row. So this set of equations is equivalent to this matrix relationship. We can write this thing as a matrix relationship, just like we did before. So y now, which has 3 elements in it, equals a 3 by 3 matrix times x, which also has 3 elements in it. We take the inverse of n, and there's the solution. It looks so easy in the matrix algebra form, but what does it look like if we actually write out what inverse is? That's this whole mess down here. This is what you get if you do that process like we did in the last video, going through and solving the equations in general. You have to do the back substitution and the cancellation. This large thing in the denominator is the determinant for a 3 by 3 matrix. And that's can't be equal to 0, or again, we have the same problem that we did in the 2 by 2 matrix. And so we multiply this matrix times this column equals the column of x's. And this is all prepared for you in the notes. And we are not going to rederive these or learn all the methods for deriving matrix indices, inverses. As far as we're concerned, just look it up. We got it in a table, a 2 by 2 or a 3 by 3 problem. We've got the inverse already set out for us. You'll notice if you look into it, though, there's all kinds of symmetries. And so you may find it easier to fill in the answer by column or by row, noting those symmetries. You're probably, I don't know whether this is even a punishment that they do in grade school anymore, but when I was a kid, I always got in trouble for various things, and they would make you write sentences just like Bart Simpson, either on the board or on a piece of paper. And rather than writing each sentence from beginning to end, I would go vertically, repeating the same letter over and over again, or the same word over and over again. You'll find that filling in matrices is much the same. If you ever had to write sentences, doing it vertically may be easier than doing it horizontally, or at least you should be paying attention to those patterns. There's deep symmetry in these because there was deep symmetry in these equations. For example, if we switch the order of these equations, it doesn't change the system at all. So I should be able to swap the first 2 rows, noting that x2 would take the place of x1, and also y2 would take the place of y1, and all of these coefficient numbers would get scrambled, but they get scrambled in a particular order. So the symmetries of the mathematics of linear algebra, linear simultaneous equations being solved, are also symmetries of this inversion matrix, which is a cool thing to think about.